Hello. Can't hear you. Still can't hear you.
Hello.
There you are.
All right, I'm glad it's working now.
Yeah, sorry. I was actually a few minutes late coming into the room.
No worries.
Just really busy. Okay, great. So let's talk. What can I help you with?
So, I've been struggling, obviously, with mostly like I understand row operations and I know how to do those.
That's good.
For me, it's sometimes like I guess understanding what the questions are asking and how to approach them.
Right. Because we keep learning new ways of saying the same ideas.
Yes.
Okay, so we have this idea of, I mean, like the big question at the beginning was, does AX equal B have a solution? Right? And then if there is a solution, is there more than one? You know, because the way we count is either there is no solution, there is one solution, or there are infinitely many solutions. Okay. And so now that we're talking about linear transformations and we're talking about matrix multiplication as a linear transformation, this language, is changing. Okay. So maybe I can just kind of talk you through some of the language stuff.
Yeah, that'd be perfect.
Okay. And one thing we can do is go through some of the problems and try to like make some notes from the problems in my math lab, because in the problems you see lots of different ways of kind of asking the same kind of question, but different ways.
Mhm.
Can I ask you this? Are there any particular homeworks that you worked on that you were having trouble with
On the
or
My
that you
Math
know?
Labs,
Mm-hmm.
so the My Math Labs I've been able to get through because once I figure out which direction to go in when I see an example problem, I'm able to replicate it and do well.
But are you remembering the language that goes along with it, right?
Yeah,
That's
so we can pick any question to start.
right. Okay, well, so shall we go all the way back to like section 1.4 and start looking at those questions?
Let me pull up my,
I'm looking at it too. Review and practice. All right, so I can share my screen too. So 1.4, you're reviewing any work you do here will not change your score. Okay, fine. So like question one. All right, so it says compute the product with the two different methods. So you did okay on that one probably because we talked about that in class at length, where there's two
Mhm,
ways to compute the product. You can do it by weighting the columns of matrix A with these as weights, right?
mhm.
Did you under or do you remember that? Or you can
Yes.
use row vector multiplication.
Yes,
Was that one okay? Did you do okay on that one?
I believe so.
All right.
I'm still.
Like here it says set up the linear combination of the columns of A using the corresponding entries in X as the weight. So, A is the matrix, this is the matrix, and X is the vector here.
Yes.
So it tells you what to do. It says set up the linear combination of the columns of A using the corresponding entries in X as weights. But
Mhm.
there's three columns, right? There's three columns and three weights. So we know it's going to be B, right? Where we put, the weight here, like 1 times the column that's 7, 5, did you do okay with,
So that question,
yeah.
I did get wrong because I wasn't sure how to format it correctly,
Okay,
and
so
then I
this is
hit,
what you have to do, right? Did you work the orientation?
yes, I know how to use the
The,
Pearson. I just like that was my first assignment, so I just did, or
sure,
I think it was one of the first ones. I just messed that one up. But I do understand what you're saying with the weights.
right, and like, so one would be the first weight, two would be the second weight, and one would be the third weight, but then we have to put in the column vectors, right?
And that
So,
would be just
you-
7, 5,
right, so you pick
3,
the number of
4.
rows, it's 2 rows and one column, because it's a,
Yeah.
right, and so, right, you just put 7, 5, right? All right, so you knew how to do this one.
Yes.
We don't need to, and the other column, 3, 4, and then -2, great. All right, so next. I think there was part 2. And B, by the
There
way,
was. I got the part 2 right.
okay. So, okay, because we kind of went over that in class, the part 2. I don't know why it's not showing me part 2.
I usually have to finish completing part 1 to get to part 2.
Okay, well then, all right. So question 2 was, this was just a reminder that if you want to multiply A times the vector X, then the number of columns in A has to equal the number of rows in the vector X, right? N has to equal T. So that was my little tip, right? That the number of so because M by N means M rows and N columns. That's what M by N means. It means A has M rows and N columns. So T by 1, a column vector, of course, is going to be something by 1, right? But the point is this T has to match this N. N and T have to be the same for the matrix multiplication to be defined. Okay, that was the hint that I was trying to give. So here, look, what is the dimensions of this matrix A? What are the dimensions of this matrix A?
2 by 3.
Oh, the matrix A is this part here. This is the vector X. See, if you read the problem, it says AX. So compute AX. So they give you A, that's the matrix here on the left, and then X is the column vector there.
Mhm.
Do you see? A is three rows by 2 columns. This is A. See, this isn't like a vertical line where it's an augmented matrix. No, no, no. This is 2 matrices being multiplied. The matrix on the left is A, and this is we call it a vector, but it is a matrix. It's a 3 by 1 matrix.
Okay.
A
So
column,
it
a
goes
column vector is 3 by, something by 1.
it goes column then row.
No, it's number of rows no, M by N means it's the first number is the number of rows, the second number is the number of columns. So this is a
Okay.
3 by 2.
Got it.
Is that what you said? I thought you said 3 by 3.
I said 3 by 2.
Oh, I'm deaf. Duh. I'm
No
sorry.
worries.
Good
It's
Lord.
okay.
So yeah, okay. So A is 3 by 2. All right, X is 3 by 1. Can we multiply A times X?
No.
All right, okay, fine. So you got that. All right, so here it says use the definition of AX to write the vector equation as a matrix equation. I'm assuming you were able to do that. Were you able to write that as a matrix equation?
Yes, but not without the example.
Okay, so right, the point is these columns are the columns of the matrix, right? And these variables are the weights. These are the coordinates of the vector Z or X. And then this is the B. This is the B on the other side. This is like the vector B. Okay, so you did get that one, great. See, I think this stuff is sort of just technical stuff in section 1.4. I don't think there's anything super deep going on yet in section 1.4. Here it says you're just practicing, write the system first as a vector equation and then as a matrix equation. So you're just practicing, right? Like the vector is going to be x1, x2, okay? And it's written vertically. So you know right now it's going to be A.
Okay.
Because we write the vector X as in vertical form. And that changes when we start talking about linear transformations. Suddenly we start writing things horizontally when we start talking about big T, you know, T of X.
How come it changes?
Because we're using function notation when we are talking about T rather than matrix notation. Like f of X, you know, it's f, you know, of X. So T is like f, but X, see, usually we think of X as just a single number. It's just one coordinate, you know, f of 5, f of 2, right? But if it's f of XY, then it's f of, you know, or f of X1, X2, then that's what gets put in the parentheses, not just a little x, but several coordinates.
Okay, so it doesn't become like a 1 by 2 vector. It stays as the
So let's talk about that. Here, let's look at that. Because this comes up in the homework that you're working on now. Okay, so if A is, you know, m by n, so m rows, n columns, and X is a vector n by 1. Okay. And if that is equal to T of X, right? So normally, you know, we write A and we write X like this, like X1, X2, dot, 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 X sub n, right? But here, the vector X isn't written like a vector. Here, it's written as an ordered pair or ordered tuple.
okay.
Okay, so that's what I mean by just notation. Okay, we write it horizontally. So let's just talk about some of the concepts that are important to understand. Okay, so let's try to translate between this idea of matrix, you know, solution and the function T, right? So just in this context where we're saying A times X is T of X. Do you want me to pin this so it's a little bigger?
Oh no, it's fine. I can see.
You can also pin it. Okay. All right. So AX equals B has, or oh yeah, and by the way, if A is m by n, then T is a function from Rn to Rm, because T is acting on a vector X that's n by 1. So the vector X is living in Rn, okay? And
As in it's spanning that.
it just lives in Rn. It's got n coordinates. It's just a single vector. It's not going to span Rn, but it lives in Rn. Like this is functional notation, like f from the reals to the reals, you know. But here we've got higher dimensions, okay?
Mm-hmm.
So AX equal B has a solution for every B in Rm. Okay, so that's a statement. But there are lots of ways to say the same statement or to see if that's true. Another way to say to see this is that when we row reduce A, there is a pivot in every row. Another way to say it is the columns of A span Rm. These are all the same ways to say this, different ways to say the same thing. Now that's just not even talking about T yet. Right now, we're just talking about the matrix A, okay? These all mean the same thing, okay? Here's another way to say it. the transformation T is onto. That's our new language. It means that over here, here's B, okay, some vector B living in Rm. And T is mapping from Rn to Rm. So here's T, but you can also think of it as a matrix acting on a vector X.
And are
So
those two like different planes, or do
they're
those
just
are
they're
just
two different spaces. It's just one
in
way
the
to
same
draw
plane?
spaces. They're not necessarily two-dimensional. I can only draw them in 2 dimensions though. These aren't necessarily planes. I'm just drawing them like that. You know, this could be R3 and this could be R2. Or this could be, you know, R3 and this could be R3. The point is you've got some. So the point is the vectors that live in Rn, they look like this. They look like they've got n coordinates, x1, x2, dot, 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 x sub n, if we write them as vectors. Or we can write them as tuples, n tuples, x1, x2, dot, 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 x sub n. Okay? It's 2 different ways to write the same idea of a vector x in Rn. The point is there are n coordinates. Okay? B, okay, B we could write it as you know a vector with little b1, little b2, dot dot dot, b sub m, because it's got m coordinates because it's living in Rm. Okay.
Mhm.
I mean, when we multiply, when A is m by n, okay, that means A can act on a vector x that is n by 1, and the result will be the outside coordinates. So that makes B m by 1. All right, so B lives over here in Rm. That means it's got m coordinates. X lives in Rn, it's got n coordinates. And the action of A sends an X from Rn into Rm. The image of X is some vector or m tuple in Rm. So there are a whole bunch of ways to ask the question. Remember that theorem that we have, the following are equivalent? Theorem 4? That was an important theorem. I'm gonna bring it up.
Okay.
Yeah, I'm gonna get it up because we talked, because it became super important. Solution sets of linear systems. I think it was in section 1.5. Let me grab it. I'll show it to you. We can even 1.6. Hang on. Yeah, oh, it was in section 1.4. Okay. So theorem 4. Okay. Says the following statements are logically equivalent. This is when A is an m by n matrix. We're still just living in matrix land, okay? All of these are either true or all of these are false. And they're saying the same thing. So the first statement is that for every B in Rm, that's over here in the range, okay, for over here, the equation AX equal B has a solution. That means for every B, you'll be able to find an X that can weight the columns of A to map to B. Every B is going to have a solution to AX equals B. Let me make this a little higher.
Okay, just to confirm that I'm understanding it conceptually, it's like those two spaces are just different spaces, and it's like coordinating like almost input output style, but they
Exactly. Exactly.
okay.
Right. The point is we want to hit B, you know, that's what it means to say that AX equal B has a solution. It means we can find it an input X that's gonna land on B. Its image under multiplication by matrix A is going to be B. No, when we multiply A times X, the result is this B. So one of the questions is, if you've got this space Rm, because that's what AX is going to map into. If A is M by N, then these dimensions of the product, A times X, are these outside numbers. The product is going to be M by 1. So B is going to be an M by 1. That's why it lives in Rm. Since A is M by N, it can only be multiplied times an N by 1 vector X. So that's why X is N by 1, because it has to live in Rn, because A is being multiplied times it, and that's the only thing A can get multiplied by, is something that has N rows.
Okay.
Now see, there's N coordinates. Each one of these coordinates of X will weight one of the N columns of A. Remember what A times X is. It's the first column of A times the first coordinate of X. Remember, A has columns. A looks like this. It's got column 1, column 2, ... It's got N columns, okay? Each one of these is a vector. Like when we see this notation, when the A1 and A2 and AN, these are not just numbers. These are column vectors. They're M by 1 column vectors. These are the columns of A. All right, so like, hang on, let me show you an example. Okay, so let's say A is this. Let's say A is 3, 2, 1, 4, -1, 5, okay? So A is a 3 by 2 matrix, okay? It has 2 columns. So we could write that A is equal to A1, A2. You see this notation all the time, where when we write A1, A2, we mean that A1 is this first column, 3, 2, 1, and A2 is the second column of the matrix big A. Okay, that's what that notation means. All right. So when we multiply A times X, X is going to have to be a 2 by 1, because A is a 3 by 2. Right, it's 3 by 2, so it can only get multiplied by a 2 by something, and since we know X only has 1 column, it's going to have to be a 2 by 1. That's our X. Okay, so we know that when we do the multiplication, where we take each coordinate of the vector X and we use it as a weight to multiply times the column. So it's X1 times A1 plus X2 weights column A2. But what is that really? It's X1 times, well, A1 is 3, 2, 1 plus X2 times the column A2, which is 4, -1, 5. So these,
Okay.
see what I mean? These all mean the same thing.
Okay,
This
and then this is just
shorthand. This
matrix
is
form.
shorthand for columns. Sorry, go ahead. What was your question? I'm sorry.
Oh, what kind of, like, what form of an equation is that, like?
Oh, this
Is that
isn't an
matrix?
equation. This isn't equal to B or anything. I'm just showing you how AX works.
Okay.
This is just understanding the notation for A times X. Okay. But, you know, this is what's called the definition of AX. This is the standard using the coordinates of X as the weights that get that get multiplied times the columns of A. Okay, this is the definition of AX. You know, this is the standard way we define the product AX. But if we want to do row vector multiplication, okay, so if we want to look at AX as a row vector product instead of using the standard definition product, so matrix multiplication, just the definition, you know, is this. Weight the columns of A with the coordinates of X, okay? So it looks like this. But the other way to do it is where we realize that we're going to get a 3x1 product, okay? It's going to be 3 rows because this is 3x2 and it's getting multiplied by 2x1. So the product is going to have to be 3x1. Like this is a 3x1. This will add up to a 3x1. But let me show you what it really looks like. So we take row 1 of matrix A and multiply it times this vector. So we take the first element of row 1, multiply it times the x1, plus the second element of row 1, multiply it times the second coordinate. So this will be the top coordinate. Well, that is what this turns out to be. X1 times 3 is 3x1, plus x2 times 4 is 4x2. You see what I mean? You're going to get the same answer either way, whether you use the coordinates of X as weights on the columns or whether you do this row vector multiplication where to get the first row of the answer. See, this is our B, okay? Now we're actually finding B, okay? The second row, you take the second row of A. To get the third row, you take the third row of A. See what I mean?
Yep.
So 2x1 minus x2, and then x1 plus 5x2. This is the same vector result as you would get here if you went ahead and distributed the x1 across these and distributed the x2. You know, go ahead and multiply each of those, scale them by x2, and then add those together. It's just, so it's 2 different kinds of multiplication, but it always gets the same answer. Just 2 different ways to get there. Turns out this is pretty important because when we have bigger matrices that we're multiplying together, like when X isn't a vector, but it's like maybe a 2x5 matrix, this particular process becomes important. We're going to learn that tomorrow. All right, so there are lots of different ways to say this theorem. This statement is talking about hitting any B in Rm. So here, let's just look at our example. Okay. So this is in R3, right? This X was in R2. So this AX in this, this AX in this example is taking, so the X is here in R2. It's a, you know, it's a 2x1. And when we multiply it by A, the result lands over here in R3 because the result is a 3x1.
Okay.
Got it?
I do got it now.
Fantastic. Because A was a 3x2, X was a 2x1, and so that generates a 3x1 vector B. So I always do this, like even now, like if I write the dimensions, it helps me so much figure out what's going on.
It's definitely a lot to remember. I can see how that helps.
Yeah, yeah. I just don't want to think too hard, you know? I don't like to think too hard. It hurts my brain. So
Me too.
my advisor used to say, I don't like to think, it hurts my brain. So let's go back to this idea of there are a lot of ways to say the same idea. Because one of the questions that we're asking is, hey, if we're looking over here in RM, and we just pick a B over here, just any old vector B that's an, you know, it's an M tuple, is there going to be an X that's going to map to that when we when we multiply it by A? In other words, is there an
Reversing
X
it.
over here that T is going to send to B? That's the question of on to.
Okay, so basically, originally there would not be, but we can make a transformation that will get X to B.
No, no, no. Either A is going to, either the columns of A will span RM. What that means is this, see, that's what it's important you understand what this means. And this has to do with pivots, okay? If the columns of A span RM, now we know that that's the size, you know, all of the linear combinations of the columns of A live in RM. The question is, do we get all of RM? See, span RM doesn't mean lives in RM. Yeah, they're all the columns of A live in RM, and all the linear combinations of all the columns of A live in RM. The question is, can we get anything in RM by using weighted combinations of the columns of A? Can A hit any B? It all comes down to the row reduction. Let me try to explain this. If we have A, let's just make it a 2 by 2, okay? So, let's just say it's A11, A12, and we can look at a particular example here. So we'll do a running example. A equals 1, 2, 4, 5, okay? I can tell by inspection that these two columns are linearly independent. That's the other thing. That's another way to talk about this. The point is this. All right, so A is 2 by 2. So A, when you apply it to a vector X, that X has to be a 2 by 1. So this is R2. And multiplication by A maps back into R2, okay? The question that we want to ask is, given any, so this is the existence question, given any B in R2, can we find a way to weight the columns of A? So this is, the first column of A, and this is the second column of A. To generate that particular B.
Okay, so the transformation helps us find other B's in the
Don't even,
R2.
nope, 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 nope. Don't even think about the transformation right now. Let's just think about the matrix multiplication, because I think you need to understand the matrix multiplication first, because you're viewing the transformation as a mystery. And it's, you see what I mean? Like you're trying to use transformation like a magical thing that's going to somehow fix a problem with A, but it's not. It is A. The transformation T is the action of A. So the first thing we need to do is just understand what multiplication by A could yield. So this is, this is a big question that we ask. That can we, in other words, is AX equal B consistent? That means, does it have a solution for every B in, R2? In other words, do the columns of A have so much power in some sense, have the capacity to generate any vector B in, in the space of the right size, in this case, R2, but it could be R. We want to think about this more generally, RM. Remember, A takes X into RM. So if A is M by N and X is N by 1, B, X lives in Rn and B is M by 1. Okay, so in general, we want to think about RM, but the point is, if you take any, so that's the question. We start with a B here in RM, and then we ask, can we find X? Can we X? We ask, can we find X that will work to weight the columns of A to produce B? Because finding X is finding the weights. The coordinates of X are the weights. Finding the X is finding the weights. Because that's
So
the
it's
way
just the
this
2
works.
by 1 in this instance?
Yeah. See,
Oh, okay.
finding the X is finding the weights that weight the columns of A to generate the B we're looking for. So when we say, does AX equal B have a solution? We're saying, can we find the weights, can we find X, because X is built up of these weights, they're the coordinates of X, that will work to be applied to the columns of A so that this turns out to be the B that we're looking for. This is B, whatever this is, it turns out that's what we call B. So like one of the big questions is, when we're looking over here, we're looking, hey, is there an X in here that's going to work so that its coordinates will weight the columns of A properly to hit a B? We want to know if we can hit every B somehow with different weights. Different X's would hit different B's. And that's the question of, well, what happens when we row reduce A? So remember, when we row reduce A, either every row of A has a pivot position, or there is at least one row that does not have a pivot. So right? I mean, you can just look at any matrix when you reduce it, if it's like this, you have a pivot here and you have a pivot here, right? There's a 0 here, and this is just echelon form. But the point is we have a pivot in both rows. Hey, every row of A has a pivot. Or if it's 3 by, there'd be a pivot here and a pivot here and a pivot here, okay? And these, I'm not doing completely reduced. I'm just doing reduced form where, these are the first the non-zero leading entries. Okay. Or maybe it's a 2 by 1, 2 by 3, pivot here, pivot here. But every row has a pivot. Or maybe it's 3 by 2. If it's 3 by 2, it is impossible for every row to have a pivot, because we don't have enough columns to have a pivot in every row, because the pivots have to march down and to the right. So here, every row has a pivot. Here, every row has a pivot. Here, every row has a pivot. Here, not every row has a pivot. So, two things can happen. Either every row has a pivot, or at least one row doesn't have a pivot. All right, so that corresponds. So we'll call this, case 1, and we'll call this case 2. So this corresponds to solutions. One. Okay, so now we are, now we're asking, see here we're asking what happens when we row reduce A. Either every row has a pivot, or at least one row doesn't have a pivot. Now, instead of asking about row reducing A, we're asking, does AX equal B always have a solution? Well, if every row of A has a pivot, then the answer is yes. If every
Thus
row,
making it consistent, correct?
yeah, if every row of A has a pivot, then AX equal B will always have a solution. But if there's at least one row that doesn't have a pivot, then no. If some row of A does not have a pivot, then there will be some B there is some B in, RM, okay, because B's over in RM, such that no X exists to weight the columns of A to produce B, i.e. AX equals B is not consistent for every B. There's some B for which there will be no way to weight the columns of A to get B. So it really comes down to A, like whether or not A can be, if the columns of A can be weighted in, in a bunch of different ways so that you can hit every B over in RM, then that's what it means to say AX equal B always has a solution. That happens if when you row reduce A, see, we haven't even looked at B or X, okay, up here. We're just thinking about A, just because A has power. Each column of A has information. The question is, do the columns of A encode enough information that somehow you can generate every single vector B some way using the columns of A, using some, here are the weights. X is the weights. The coordinates of X are the weights. And so whether or not you can hit every single B with this matrix multiplication really comes down to the power of the columns of A. Because if the columns of A aren't powerful enough, then there's going to be a B that you cannot generate using the columns of A because the columns of A aren't powerful enough. So when we do a row reduction, we're really measuring the generative power of the matrix A. In other words, we're taking a measure of how powerful those columns are. Are they powerful enough that we can get every single vector B possible over here in Rm? If so, that's going to look like having a pivot in every single row.
That makes sense.
Does it? I'm so glad. So once you understand that really it's A, it's the nature of the matrix A that determines what vectors can be hit, under matrix multiplication, or what vectors can be generated by taking the columns of A and weighting them with different weights. It's really it's all inside A. And the transformation T is just another way to talk about A, but it really is the same thing as multiplication by A. That's what we mean when we say A times X is T of X. That's all we're saying. We're just saying, hey, we know A has columns. Its columns encode information. Maybe that information is enough to build the entire space Rm. Maybe. And the way that we build the entire space Rm is by using the weights in the X's that we're searching for. We're searching for the weights that can be applied to the columns of A to generate B. So when we think about T, when we say T of X equals AX, we're simply saying T does exactly what A does. And T is being viewed as a map from Rn to Rm, where T of X is a function, T of X is matrix multiplication, and it's a function from Rn. It takes X's and it maps them to B's.
Okay.
And so we had two new definitions. T is onto if given any B in Rm, there is an X in Rn such that T of X equals B. But that's the same thing as saying AX equals B always has a solution, because T of X is multiplication by A. It always has a solution for any B in Rm. These are saying the same thing. T is onto means AX equals B always has a solution, but that means A has a pivot in every column when we row reduce it. These all mean the same thing. I'll post these notes, okay?
Okay, I appreciate it.
There'll
Thank
be
you
a
so
class, and
much.
I'll post this video too. But this is just the start. We need to have numerous conversations in order to really kind of get coverage on the numerous things that are going on. This is just the very beginning, because this is sort of half the story, because we're also talking about the idea of one-to-one. But let's just start with onto, okay? And then one-to-one is another function property, and it's related to AX equal B having a unique solution if it exists. And uniqueness of the solution comes down to not having any free variables. But whether or not A has free variables comes down to just A itself. We row reduce A and we can figure out if there are any free variables that would exist if we used A for matrix multiplication. It comes down to row reduction. See, A is A, and all of what A can do, multiplication by A, all of that is all in A. And we discover what A is capable of generating by row reducing it, looking to see if there's a pivot in every row, and also looking to see if we look at AX, if there are any free variables. So we haven't even started to talk about free variables here. Okay. But it's I've been working since 9 a.m. this morning, and I've taught 2 classes and given several office hours to several different people, as well as a regular office hour, and had other meetings, and I've got to call it a day.
No worries. I think I'm running at my max as well.
Okay.
I will email you about Friday and you can let me know when your availability works. Thank you so
Okay.
much for the help. It definitely did clarify a bunch of things.
Good. And if we have to meet on Saturday, would that be okay?
I can, I have an event on Saturday, but I definitely can be there in the morning.
Okay. So we'll see. I've got a big fat deadline that's slapping me in the face. Hopefully
We
I can
always
get
meet Sunday if that works better for you.
Sunday always works.
Then let's plan for Sunday.
Okay. And like I said,
Thank-
I'll post this video in a new playlist. I don't remember if we have a 265 office hour playlist yet or not on YouTube, but I'll
Thank you.
post this video.
All right. Thank you so much for your help. I really do appreciate it.
Thank you for coming by. I hope this helps several people. Okay.
Thank you. Bye-bye.
Good night.